Hi, I'm Sriram, and in this video, I'm going to talk about RNNs, LSTMs, and the shortcomings, mostly in the context of NLP. So, a typical feed-forward neural network takes one input and gives a one output. So, in order to give a prediction or an output, a neural network looks at only one input at a time. Oftentimes, this is not so useful because you have periodic nature of your data. There goes a saying that says, "Those who forget the histories are destined to be doomed." What does this exactly mean? That means, in order to make a proper prediction for the future, to make an informed decision, you often have to resort for analysis of the past. Only through the history you can make an informed decision about the future. The same principle goes within a recurrent neural network. So, look at this diagram. You have a curve that is having some periodic ups and downs. You can only observe the long-term nature of this by looking at multiple inputs at a time. In other words, you look at a sequence and you observe the periodic nature of the sequence. That's called looking back in time. Now we have a recurrent neural network. And how exactly we can interpret this? A simple way of looking at this is unrolling the neuron back in time, one step at a time. As this diagram shows, we have a neuron, which is the basic building unit of a neural network. It's taking in one input at time step 0. It produces an output y0, uses that output back as an input for the next time step. So at time step 1, the output is not based solely on the input at time step 1, but also on the output of time step 0, that is the time step before it. This is just a simple case where we are looking one step backward in time at each time step. You can also have neurons that look at 5, 10, or maybe 15 steps backward in time, depending on the size and the complexity of the periodicity. So, in short, our RNN is all about looking at sequences, looking back in time, and also looking at variant lengths of sequences. A typical feed-forward neural network, on the other hand, can only look at one input at a time. But in an RNN, you must have the capacity to look at variant sequences at a time. Because let's say you have a sentence. A typical sentence may be having about 10 words, and based on the tone, if you have a more casual sentence, you may be having a fewer number of words. In order to have a robust system, an RNN is designed to be capable of handling multiple lengths of sequences. You have two sets of weights, one for the regular inputs and one for looking back in time. So, now what exactly are the problems with RNNs? As with any regular feed-forward neural network, there is the problem of vanishing and exploding variance. This happens whenever there is a difference in the variance of the inputs and outputs at a layer. Let's say the variance is greater than 1. That means the outputs are diverging. So as you go deeper into the network, as you have more layers, the divergence keeps compounding, and that leads to an explosion. The reverse may be true as well. Let's say there's a convergence. By convergence, I do not mean reaching the optimal thing. By convergence, I mean there is a reduction in the variance. There is a reduction in the range of values that are being covered, layer to layer. As you go forward, as you go deeper, the values keep shrinking and shrinking. The effect is compounded until a point of time where the weights actually vanish. There's no point in having the weights then. There's no information being held. With RNNs, however, this problem is much more exponentially greater because for one input, you are looking multiple time steps back in time. And in each of these time steps, the weights are remaining the same. That is, the weights are being shared. So the same weights are compounding on the same input at multiple steps of time for each input. Because of this, there is a higher compounding of the effect of weights. And thus, let's say if you are going back 10 steps in time at each layer, a recurrent neural network would be exploding or vanishing the gradients 10 times more at each layer. So you can only imagine what happens if you have like a 10 or 100 layers. The amount of vanishing and the amount of explosion happening is exponentially in nature as compared to feed-forward neural network. And hence, you cannot create a very deep neural network with RNNs. That's a huge problem. And also, an RNN fails to capture long-range dependencies. Because it takes data sequentially, it only looks at the data sequentially. That is one at a time. But it cannot look at a long-range dependency. Sometimes the first word of a sentence may be contextually valid or important for a word that is like in the next sentence, maybe. An RNN cannot do that effectively. And with this sequential processing, we have two problems. One is the inability in pattern recognition, as I just explained. There is no contextual dependence that is not sequential. And also, there is a problem with hardware acceleration. Because the RNNs are processing data sequentially, they cannot take advantage of the GPUs. GPUs are hardware devices that can take advantage of parallelization and exponentially reduce the training time and highly optimize your performance, the training performance. So this is possible only when you have something like a matrix operation going on. A sequential operation cannot be parallelized. I mean, the name itself says it's sequential. So by Amdahl's law, the sequential component is much higher and the amount of speed up you get through a GPU acceleration is too low. So you cannot take advantage of how much of a hardware you may be having. And because of its inability to recognize patterns, the output of a RNN cell is highly biased to its most recent outputs. That is because of its limited memory. It only processes sequential data. Let's say it is processing 5 time steps back in time. Then it can then the output is only dependent on 5 time steps back in time. But there may be a longer dependency that is maybe 10 steps behind in time. And RNN fails to do that. And also, there is no selective memory control. Sometimes there may be inputs in the sequence that are not so significant or not so important. An RNN cannot distinguish between an important and an unimportant thing to be kept in memory. That leads to certain kinds of biases in the processing that happens. And now let us discuss more about the vanishing and exploding gradient. So here this diagram shows how a typical RNN cell is going back in time. Here, the weights and biases are the same. So, in one step of a back propagation, these weights and biases are all changing at the same level. So, at a particular point of time, the weights here and here are the same. You get an input. Let's say the input is reduced by a factor of zero point 0.5. So, it becomes 0.5x here. When it goes here, it becomes a 0.25x. The next, it becomes a 0.125x, and so on and so on. As you go further back in time, there's a much more diminishing happening. The converse is true. The magnification may be happening at an exponential scale. That is a very costly problem. We cannot build a deep neural network out of this. So, you may be thinking, why don't we use something like a batch normalization? A batch normalization is the common use technique in a feed-forward neural network to deal with the difference in variance of the inputs and outputs at feed-forward layer. But with an RNN, when you do that, it breaks the sequential structure. So the point of our RNN is to capture sequential data. And if you are using a normalization to break the sequential nature, there's no point in having it. It fails to perform well. Why not use a layer normalization then? Well, that is a good alternative, but this does not stabilize across time step. A layer normalization will help you do perform well at a particular time step, but you consider the next input, or you go back 10 steps back in time. A layer normalization is not going to handle the vanishing and exploding gradients well. Why not use gradient clipping then? So if there's an explosion of gradient, just clip it. It won't explode further. Just clip it. So obviously, this only solves the exploding gradients problem, and sometimes it may also break the relations and structures between different contexts. It does not solve the vanishing gradients problem anyway, so this is not a good solution. So what to do now? We go to LSTMs. And LSTM is an improvement over a typical RNN cells. It improves over the shortcoming in RNN. The main important feature of an LSTM is its gates. So let us look into its structure. As you can see here, we have a LSTM cell. Unlike just the input and the output state at an RNN, you have many things going on here. One thing is the C, which is the cell state, and the other is H, which is the cell's short-term state. And then you have an input just as always. So this cell state is something that carries information across long sequencing. That means it holds the aggregation of information over a very long sequence. Historical knowledge, perhaps you can say. The H is going to store the most recent information. So it's like a caching of the recent sequence, you can say. A more updated information. But it's not as valid or as historically important as a cell state. So the point of gating is to control the information. What information is to be retained in the long-term state? What information is not going to contribute to the long-term state? Let's see how that happens. As you can see, we have sigmoidal gates here and a tanh gate. The first sigmoidal gate is called the forget gate. What the forget gate does, as its name suggests, it tells you what to forget from the long-term state. It takes in the input and the short-term state. And if the input happens to be something disruptive or something very important, something unseen, something that contributes to the pattern recognition, there's going to be a significant change in the long-term state. The sigmoidal gate here, it's going to output a value between 0 and 1. So you can think of it as a fraction. So this ft is going to give you a number between 0 and 1. That means, let's say the number is 0.97. So the output is going to tell only 0.97 fraction of the CT minus 1 is relevant for the long-term future here on after getting the current input. If you have a very less significant input, something that's relatively invariant, something that's not contributing to get the long-term pattern, there's not going to be much change. It's going to remain as 0.99 CT minus 1 or something. And then, let me adjust this. You have the input gate here. The input gate tells what fraction of the current input and the current most recent memory state is important for the long-term state. You extract that. Again, there's a model function. You get a value between 0 and 1. That tells how much of the most recent input and the current state are important. It gives you that. And then the tanh function. That's not going to give you a fraction. It's going to give you a value between 0, minus 1, and plus 1. So that's going to tell what portion of your current input and the current short-term state are going to contribute to the long-term state. You add them up and you push them into the long-term state. As you can see here, all operations are additive, unlike the multiplicative operations in the backpropagation step of an RNN. Because of this additive nature, the vanishing and exploding gradients problem is averted. And then you have the output gate. The output gate is going to say, okay, you have an input here and you have the most recent memory state. How important is the current input to the most recent memory state? and it's going to kind of mix them together and give you an new short-term state, and you have a updated long-term state. This is how an LSTM works with sequential data. Gating prevents unstable variance by using iterative updates. I explained how. So if it's all well and good, what's the problem then? While the additive nature are going to alleviate the unstable gradient problems a bit, it's not avoided completely. And also, the retention of information here is happening purely mathematically. There's no contextual information in the sigmoidal and tanh function that's going to tell which information is important, which is not. Everything is a purely mathematical disruption that is going to take part in the decision. That's not going to hold up well with a typical NLP task where context is very important. And then, just like with a typical RNN cell, the sequential processing, it's a problem. You cannot make advantage of hardware acceleration, and also you cannot look at long-term dependencies. And also, because each cell is holding two things, a short-term state and a long-term state. Now, consider having a neural network with 100 neurons. That's a relatively short cell in comparison. Even that is going to take up a significant amount of memory. It's going to be computationally expensive because you have to pay for more cloud storage. And that's actually going to be in the RAM. Unlike a regular information, which can be stored on a disk, you want the weights and biases and all this information and all the memory state to be stored on a RAM or an unified memory, for instance. That is going to be extremely expensive and very limited computationally. You want the RAM to be filled with computational useful information, and when you're having just redundant information all over, that's not going to be contributing to your performance, and it just takes up storage. And now let us look at some other more NLP based shortcoming. Long-term dependencies and context, those are lost. Everything is purely mathematical. Let's consider a typical example. There's a cat on a wall. I hope it's a cute cat. You have like maybe 400 words in the sequence. And then you have a sentence. The animal on the wall is one-eyed. We humans are good with pattern recognition, and we grow up all listening to stories. So we can understand that the animal on the wall is the cat that's mentioned in the first sentence. But LSTM is not capable of storing this amount of aggregate information because everything is being stored mathematically. The individual contextual information of words like a cat on the wall, all these are being lost in the sea of words. And also, again, there's a word order of differences. When you're translating from one language to other, typically there won't be a word to word corresponding in the translation. We'll look at an example on that. When you're going with text summarization, when you're summarizing one word at a time, sequentially, how can the summarization be accurate? Because the context and the story entirely might be changing from one sentence to the other. You want to capture the long range contextual information. Without that, the summarization is going to be highly ineffective. And when this ineffective summarization is happening, and the long term state is holding an ineffective summary, that ineffective summary is going to be used again for the new input to create an even more ineffective summary. So the errors only keep compounding. The problem gets even worse with longer text. So LSTM is not suitable for long range NLP tasks. Again, there's a lack of memory over long context. You cannot retain very huge information like a huge story or a thesis document or anything of that sort. And also, because everything is happening purely mathematically, there's no particular importance being applied to certain words. There may be something like words that is destruction, and there's a word called annihilation. Both words mean different things in different sentences, but sometimes when you're talking about some species or natural order disruption, they mean the same thing. But the intent of the words, that's not being taken into factor by an LSTM mathematically. But the importance and the context information is what makes NLP a natural language processing. You need the contextual understanding which is being lost. And also, as demonstrated with the cat example before, when you have a lot of pronouns, so the same words are being repeated again and again. The LSTM is going to fail to capture what pronoun is referring to what entity. Let's say you have a long sentence. There are multiple instances of the pronoun he or she. When you have multiple people, it may fail to recognize that, okay, this he is referring to this particular entity. This she is referring to that entity. That information is not preserved mathematically in the getting mechanism, hence not suitable for NLP. Now let's look at a more comprehensive example. Uh, this is a statement in Japanese that says, Uvesami Narimshitam. I hope I'm pronouncing it right. So this is a Japanese statement. When you translate this word to word to English, it translates as I become your care. Okay, that's a well-formed English statement. You can think it has some meaning. But when you look at the actual translation, it's going to say, thank you for taking care of me. These two mean entirely different thing. An LSTM or an RNN cannot capture this out of word dependencies, out of order dependencies. For that, you need something that can put more attention on a word and see how important it is to some other word. See how linking, you have dynamic linking that tells how one word is attending to the other. So I think you know where I'm getting at through the kind of attention mechanism and eventually to the transformers. That's a topic for another video. I conclude this video by telling you that although RNNs and LSTMs are built to deal with sequential data, and they're quite often used with simple NLP tasks. And before transformers came into picture, they were the de facto standard. But now you have long sequences of data being processed, being translated. You have YouTube videos being processed. An interesting example is the recent Lex Friedman's podcast with our Honorable Prime Minister, Sri Narendra Modi ji. That video was actually recorded in English, but an Indian startup called Servam.ai has translated that into multiple regional languages of India. How is it possible? You cannot possibly translate a 3 hour long video. There's a lot of data through RNNs and LSTMs. A transformer was used. A transformer based technology was used to do that. And so I conclude the video now. Thank you.